Hello everyone. Today we're gonna talk about the profitable way to find vulnerabilities in client-side web applications, presented by me, Youssef Sammouda, cybersecurity researcher and consultant. First of all, table of content, as you can see below in front of you about me, bug bounty hunting, requirement to enter the bug bounty hunting field, and lastly vulnerabilities in web application in the exactly in the client side. uh, about me, I started the field of information security 5 years ago. After learning and applying my experience, I focused on trying to help emerging and global companies to patch security holes in web and mobile applications through bug bounty programs mainly, and also doing security consulting for private companies. I found more than 120 security vulnerabilities, thanks to God, in companies such as Facebook, Vimeo, Tesla, and Quora. Most of these vulnerabilities were in Facebook, and most of them were critical, which made me ranked first in the Facebook bug bounty or white hat program in the last 3 years. Uh, Here you can see some of my most critical vulnerabilities. As an example, I found a security vulnerability that allowed me to show the content of error messages and internal exception due to defect in deleting some Facebook objects. The content of the exception was information about each object, such as Facebook user or company infrastructure. I got $81,000 for this bag. Also, several loopholes enabled me to read internal files from internal CDNs. I got 45,000 for this one. Also a bag that allowed me to steal personal information of any user, such as private photos and messages. This one was due to the ability to create access to API access token for any user, Facebook user. Also, several loopholes allowed me to hack Facebook account by deceiving the user to visit a specific link that exploits a loophole against him or a bug against him. Today we're gonna talk about this type of bugs, mainly client-side web applications bugs, and yeah. This is the annual ranking of the Facebook Bug Bounty program. This photo of me and my team members at a global competition organized by HackerOne. How and the requirement to enter the field. It is rumored that this field is for everyone and you only need a limited knowledge of some concepts and attacks to enter it. And this is a common mistake and it should be noted. The bug bounty field is not much different than the field of application security engineering or penetration testing. It is true that in this field you are not under management or of, for example, of higher authority, which may blame you when making a mistake, for example. But this does not mean that you are completely free to enter the field without prior knowledge or study in order to succeed first and also to get good like a good reputation that enables you to work in international companies later. Uh, we'll try to give some requirements to before entering the field, and which I personally see as necessary. First of all, programming, like because vulnerabilities are errors or malfunctions in in the application developed and directed to a specific category of customers. You must understand the software codes and functions in them to be able to detect places where a feature can be abused. And this is actually the bug. Although most companies do not publish the source code of their applications, if a security researcher is familiar with programming and the widespread methods to program a feature or a function, he can predict the possibility of some errors and then directly search for them. The best example of the importance of understanding some programming languages and code is the type of bugs or vulnerabilities that I will present today, which depend a lot on understanding the programming language, JavaScript, and the HTML markup language. Of course, here, if you're interested, for example, in web applications security, you may try to learn about PHP or learn PHP or JavaScript, or even only JavaScript and its applications in client side and the server side, like Node.js. If you're interested in mobile applications security, you can learn about Java or Swift for Android or iOS development. Uh, Learning approach. The approach to learning how to find vulnerabilities is, as we mentioned, first knowing about programming and various functions, protocols, and the internal technology used. Here, for example, databases or LDAP, or I'm not sure what else. SOAP, for example, used and how they work with each other internally, and then studying what types of attacks that could be launched against these, and knowing what are the possible vulnerabilities that could occur before knowing how to find or exploit them. Among the most important sources of knowledge, to my belief, are like to learn, first of all, to learn attacks and attacks techniques. There are books, write-ups, and security white papers. While reading these resources, you must apply what you have learned and continuously and immediately practice in order to be able to further understand and study other cases of how, like how a vulnerability exists or how to exploit it. Also, the best ways to train, to my opinion, is practicing, participating in CTFs, doing labs like Portswigger labs, and also hunting in VDPs programs, vulnerability disclosure programs. Here are some resources and references. Importing blogs and websites, also some books that I'd recommend to read, very interesting ones. Here are some security experts on Twitter, also I'd recommend you to follow them. Also practicing here, you can find like CTFs, HackerOne, VDPs programs, also OS vulnerable web application. As one of the ways of learning is to try to program applications that are intended to have a particular bug, and then try to exploit the bug yourself. Perhaps this will not teach you how to find the bug, but will help you improve your exploitation skills. Also some books, guides from OWASP on how to find and avoid security bugs. Very good resources. Some links to report bugs in different websites like Facebook, Google, PayPal. Vulnerabilities in client-side web applications. Web applications on the client side are a set of codes that are written in JavaScript, which are received by the browser in the form of a text, and then we can say compiled and run for performance here. This enables us to do complex things on web pages, like every time a web page does more than just sit back and show you static information, like how it was back in the 90s, I think. But these programs allow developers to update content in time, show interactive maps, for example 3D animations. With these features, several security challenges arise to ensure the safety of information and customers. So far, I have tried to explain most of the terms and concepts that we pass on, but understanding the following attacks requires some simple knowledge, such as the content of messages in the HTTP protocol and its format, also knowledge of JavaScript and the two markup languages, HTML and CSS, also like parse names of the link or URL. Here are some important terms to understand the attacks. The DOM, it's found in JavaScript, which is the model of representing the page as an object or document object model, as it's called. Um, and it contains all the component of the page in the form of objects as well, and it is considered one of the basic methods for building interactive websites. Source, any Java, this source and sinks and are like terms we use in exploitations of like Css attacks or prototype pollution attacks. So the source is any JavaScript feature or function that accepts data from the user. Simple definition here. Async, any feature or function in JavaScript that consumes the data from the source in an unsafe manner. DevTools, a set of tools in the browser that enables you to analyze and modify the content of the page and watch the process of running JavaScript codes. URL query, it's the part of the link uh, between those two, like exclamation mark and the hash. The URL fragment hides the part of the link after the first hash. Uh, what's next? So the first attack here is prototype pollution. Definition JavaScript depends on the prototype. When new objects are created, they will carry properties and methods of the object's prototype or the inheritor object prototype, which contains basic functions such as toString, constructor, and has own property. Object-based inheritance gives JavaScript the flexibility and efficiency that web programmers have come to love, but also makes it vulnerable to manipulation, or in this case, prototype pollution. There are several ways to discover the prototype of an object. For example, using this method, get property prototype of. Here, as the example here we have returned the prototype of almost every object in JavaScript, which is object with a capital O. When accessing a property of an object via x.name, it actually does the following. First, the JavaScript engine searches for the name property of an object of the object X. If present, it is returned. Otherwise, the prototype of the object X is selected and its properties are searched to find X. The inheritor in turn has a prototype, also its parent inheritor as well, and so on. This sequence of prototypes from object to null is called a prototype chain. In the case of object X, the chain is short, like in the example here. X is an object like we created X before, like here. X.proto, for example, here there is a typo. X.proto would give us null, since the chain is would only contain one prototype of the parent, which is object, the main object. Malicious actors can make application level changes to all objects, like by modifying a single object, hence the name prototype pollution. In this case, the attacker doesn't even need to modify the object directly. They can access it through the proto property of any object in JavaScript. Um, Once a change is made to the main object, it applies to all objects in the running application, including those created after the pollution. Here another example. We have an object called person. We first console.log the toString, the result of toString function. Then we access the prototype of person and override toString function to do an alert contain change. We later recall toString function of person, and we note that now we have an alert contain change instead of as before object string is shown. Here we define object administrator contains two properties, name and is admin set to true. Normal user name me is admin false. Here is more of a server side example where each user has a property called is admin, but it can happen in client-side applications, I think. Third, user, an object not identified user, empty object. We first console.log normal user is admin, which should be false. Also, we try user is admin, which is undefined at this point. Also, we now access like we try to access the main object by accessing the prototype of window. We try to reach the object, the prototype of object, but from the window object, and add is admin, set it to true. This should like replace any in the any object where is admin is not set. It would replace to true, or be set to true to be more accurate. Later we try console.log user is admin. This was undefined, but now since if is admin is not found in the user object, it would JavaScript would look in the prototype, and in that case it would find is admin and set to true. Also, normal user is admin. It was false since it's present. It's a property of the object normal user. It would return that property value and not the one from main object. Vulnerabilities and attacks. We can use prototype pollution of an object to launch many attacks. For example, to achieve DOM cross-site scripting, and here it is possible because the client-side code and not due to lack of filtering when returning data from the server. After manipulating or adding properties of some objects, we can extract data for the user or session. What do we need to attack? First, we must find a code with a weakness that allows us to pollute the prototype. Initially, we should find a source, which is any function that saves data coming from us. Then we follow how the data was used, and is there really a code with a bug that would allow prototype pollution. Fortunately, there is a pattern in the codes to find this vulnerability, which makes it easier for us to search. After polluting the prototype, is there any application logic or function that could cause malicious JavaScript to run or to be run or to extract data? This process is called finding a vulnerable script gadget. Common sources that we control. We have window.location.search, the query part of the current URL, location.hash, the fragment or hash part of the current URL, cross-window messages via sent from the attacker page via post message. Of course, the targeted page should have an event listener listening for cross-window messages and using these messages safely. Document.referee, the previous link that redirected or who referred us to the targeted page. Also form inputs. The inputs on the page, but it's very rare to happen. Some patterns in codes like vulnerable code. Common functionality in the application that might cause prototype pollution is the merging of properties of two or more objects. This process is called merge. As you may notice here, this code is a recursive function that would copy properties of object source to target. Here, an example to using of polluted objects. Actually, this code present a vulnerable source and sink. The vulnerable source is a get tracking attributes functions. For example, here is an example of code that takes data from the link, the current URL, and converts all this data as a key and value pair onto an object. Here is the object tracking data. And then adds or combines these properties with the properties of an element in the page document. Not exactly an element, but any object here called element object passed as an attribute, as an argument to get tracking attributes. But in this application, a document element was passed. This leads to the ability to add and run JavaScript codes after adding inner HTML contained in the current URL. Of course, we don't actually need here to pollute the prototype object, but like we can use this and then look for script gadget elsewhere in case we didn't have the possibility to with the element with the merging with an element object. Ways to find this vulnerability. First of all, attempting to review the source code and search for potential sources using keywords such as, like we mentioned this before, location.ref, location.hash, location.search, document referee, and verify if they are used in a merge or other similar operations. To be honest, this is the most difficult method. The second method is programming or using tools that inject the important places in the links with the payloads, and then verify the success of the pollution or contamination. We have some tools here like ppscan and selenium boat. Second, we can check if the polluted object has been used by manual scanning after searching for keywords like source doc, inner HTML, iframe, create element, or by using tools such as pollute.js or untrusted types. Here, an example of vulnerability found of this type prototype pollution in the HackerOne platform. Full article could be found here, of course, the URL for this report. HackerOne, actually the subdomains www use JavaScript to display videos from platform Wistia, called Wistia. Some lines of the code used. We can note we can notice that location.ref and document.referee were read, and their content was placed in the variables u and t. This is a potential source, both of them. To make sure that we have here the possibility of prototype pollution, we put proto test equals val in the link in the current URL, and then check that the test element has been added to the object prototype. If not, we can try with the proto test, for example, and so on. The researcher found test, which means that the prototype of object has been polluted after polluting object. We should now find a script gadget, any function that uses the polluted object in a dangerous process. Her researcher find a function named element from object, which creates an element in the page like a new tag and adds attributes from the object passed as argument to function. Of course, to the function element.from object. Since we have polluted the prototype, for example, with test, any object will now load the test element, and thus the object passed to element from object. Here the researcher, of course, has added HTML and JavaScript code in inner HTML instead of test via the current URL, which means that any element or tag on the page will have the inner HTML. Any, actually, have to be accurate, any element object in the page will have the inner HTML from the attacker. To those who don't know, inner HTML is the literal writing of the element, and that will be placed in the page. Here, the researcher was able to get the DOM XSS. Here, the code to use element from object. As you can see, this object with with properties like ID, class, style, tab, index was passed to that function. Of course, here after the prototype was polluted, this object would also contain inner HTML, and thus would lead to DOM XSS. Here is the link to exploit the bug simplified. As you can see, it accessed inner HTML, proto inner HTML, and a simple script to execute alert one. I think in the original report, uh, uh, CSP bypass was needed. This shouldn't work. Next, we have another vulnerability, DOM XSS. DOM XSS is type of XSS attacks when the payload is executed as a result of modifying the DOM environment in the victim's browser by abusing the application on the client side, so that the client side code runs it and runs in an unpredictable manner. That is, the page itself, like the response from the HTTP request, does not change, but the client-side code on the page is executed differently due to the malicious modifications that occurred in the DOM environment. We check that the information coming from the source is going to error. We can, like, the way to find this vulnerability would be to check that the information coming from the source is going to dangerous places or functions that led to the possibility of attack. These functions are called, as we mentioned before, called sinks. Here are some examples of sinks functions. Sinks functions. We have document write, document domain, location ref, element inner HTML. Also some examples of sources, vulnerable sources, of common sources. Example one, the following code, as you may notice, reads the content of location search via the URL search params function and lets you create an object from the content. This is the source part, and securely passes content to name lm.inner.html, which changes the content of the element in the document. Here the sync part, of course, here we can achieve DOM XSS. Example two, the following code writes to the page or document without an escape action. Escape, or we here mean to remove or encode HTML characters. And the content is from a source controlled, of course, by the attacker, which is location.ref, which is the current URL, or in other words, the current URL of the page. Third example three, the following code reads content of document referee and creates an object from it. Source part here. It then checks for a property in the object called initRedWays, which is a field in the query part of the link. And if found, moves the page via location.ref to the properties value without making sure if the link starts with HTTP or HTTPS. Here the sync part, which allow us to use JavaScript to enforce the redirect to to a JavaScript link and achieve DOM XSS. Tools that can be used to facilitate the search process, DOM XSS here or DOM snitch, also important references. Next type of attacks, website attacks. WebSocket is a protocol in the web similar to HTTP and differs in the way the communication between the server and the client or browser happens, and its speed. The main difference here is the speed. WebSocket is near real-time communication protocol. The switch to using this protocol is done after presenting the page of website via the HTTP protocol, and then using an API in JavaScript that enables you to establish website connection. Attacks, the server checks the origin of the request via the origin header, of course sending the HTTP request, and compares if the site that sent the connection request is whitelisted. Of course, the check here is done server side. Course security feature does not apply with WebSockets, unfortunately, which means that cookies are sent whatever happens in the initial request, and the majority of server-side applications would use received cookies to identify the current user and also to resume the HTTP session in WebSocket. In summary, here is the application of the server fails to verify the origin and later use the cookies sent to identify the user and return his data in a message. This means that we can, from our website, talk to the server and steal information about other site user, other website user. Example here. Here is an example of a code that opens a website communication channel with a website that does not check the source of the request of the origin, as we mentioned before. Cookies are also sent here, which means that the users of the original website, when they try the page, when they visit this page hosted in the attacker website, with the following code will be vulnerable. They'll be vulnerable to be attacked. We send a message informing the site to return user data as we here get profile, and we wait for the response with the data here by setting up the listener on message, the on message event listener. Of course, here the message sent can be to change your password, but it's not very common, to be honest. Or, for example, to return an access token used to use the website API. Here, a tool that can help you debug the website communication. You can specify a target to connect to and check if it accepts this origin. You can play with this. Here's an example of vulnerability I found in Facebook of this type. This vulnerability allowed me to take over Facebook accounts of users in my local network only, and also phone users or mobile users who installed malicious application I own. The vulnerability simply appears because the Facebook subdomain, which was using WebSocket instead of HTTP for communication, was allowing local IP addresses to be legitimate origin to establish a connection via WebSocket. So here, if the request to establish WebSocket connection was sent with the origin header from a page that has a local IP address, it would accept this request and establish the connection. Of course, as we mentioned before previously, the browser sends cookies, which allows the server to use them to identify the user and send him his personal information. This happened too of course, with Facebook. The following code is exploitation code, which should be hosted on a page with a local IP address like this one. We cannot target any user, unfortunately, with this bug because the local IP is only available to users of the same network. So this vulnerability targets Facebook users in the local network, like your home, workplace, or restaurant, or university, for example. The vulnerability was patched by ignoring cookies when the request is from a website with a local IP, so cookies won't be read and it would ask you to log in again. They did not reject the local IPs instead of the other solutions because they actually used this internally for debugging. I got $12,500 bounty for this bag. Also, you can find the full write-up here. Cross-window messaging attacks. A definition, cross-window communication allows applications running on different domains to communicate in a secure manner before entering messages via Windows or before introducing this API. Communication from different origins and domains between iframes, tabs, and windows was restricted by the same origin policy and enforced by the browser. The developers used many hacks in order to accomplish this task, and most of them were basically insecure. For example, trying to communicate using the window.name, using Windows name. The messaging API introduced a post message method through which regular text messages or more complicated messages can be sent across different domains. It consists of two parts: the message and target domain. Of course, here there are other things like transferable objects, but we won't talk about these today. To receive messages, the receiving website needs to add a new event handler or event listener, sorry, and the next event has to the following. Sorry, there is some confusion here. So the event listener should be listening for messages or cross-window messages, and the function handling the received message would receive like data, like the content of the incoming message, origin of the sender, which is the origin, also the source, which is the window that sent us the message. Here is a simple code to send a message, cross window message. Here is the origin that the message is allowed to reach. Message is the message contained. Opener is the window that will receive the message. Here the opener represents the window that opened the current window. If esam.com is not open in the opener window, then post message will not send the message. Okay. Here's an example code to receive a message. Here we have the handler used by add event listener for messages. The handler would check the origin of the message sender. Here event origin should be www.google.com, and also the event source should be the window opened, which is the window that we previously opened. Add event listener, we said we already talked about this. Okay, I hope you understand this code. It's very simple. Attacks, the previous codes are examples of the correct use of this feature, as we check where a message should be sent, and also in the other window we check the source of the message that we received, and also the window or the source it sent. These checks are important and if they are missing, or this means that we have a vulnerability that can be exploited to launch any attack, basically. Here, an example of code that never checks the source of a message. It doesn't check neither the source or the origin. It would set the inner HTML or set the raw content of the element, the element to anything basically received in the message, to be precise the document property of data which is the message received. Of course, that the message could be a string, could also be an object, any clonable object, basically. Here, this code is an example of code that checks the source of the message, but in a wrong way. Here, there is a bug in the regex because it misses an escape dot. Like before, here we have an escape dot before com, but we don't have one before Google. So here it was intended to match google.com, any subdomain of google.com. However, because of the missing escape dot, an attacker can use any domain or register a domain like anything here, google.com, and messages will be accepted from this domain. And of course, here we can achieve XSS, DOM XSS. Here, a vulnerable code that would basically send a message containing the information, personal information of the user to the opener window without verifying the target origin, or if we want to send this message to specific origins only. Also, it's not recommended to use the star at any cost, of course, because it's not secure. An important tool that will show you if there are event listeners for cross-window messages in the current page. Post message tracker, great tool by the great France Rosa. Example here of a bug that I found in Facebook exploits the same bug that we talked about. The following code was found on Facebook page. It would create an event listener for cross-window messages and would wait for a message whose sender has a domain or origin owned by Facebook, like for example www.facebook.com or portal.facebook.com. If a message arrives from a valid domain, as we mentioned, it creates a form and puts the action attribute of this form from the message received. Here they checked the source of the message correctly, but failed to filter the message content or how to use this message content. Why is that? Because here, if we put the action value to a JavaScript link, we can run JavaScript codes. Of course, there are no CSP rules that made us unable to do that. Of course, we cannot do that so far because messages are only accepted from Facebook domains. In order to be able to exploit the bug on the previous page, I must find another Facebook page that sends a message whose content is controlled by the attacker or by us, a page with the this specification has been discovered that used the query from the link on the server side to return a HTML page with this code. For example, if we specify test equal test from us, like here the part here in red, we notice that the response would contain a JavaScript code uh, with test set in post message and sending that message to opener. We can now send messages from a facebook.com domain, and we also control the content of the message, so they will be accepted on the previously mentioned page. Of course, before that, we should establish a relationship between the two windows or that host the two pages, page proxy and redirect.php. This could be established using this piece of code. It's very simple. We first open, this is an attacker page. When the victim clicks on a button, it would open payments redirect.php. Then instantly it would redirect the current page to page proxy. Of course, this page, this vulnerability was found before corp was set in was used in Facebook. Here is if we put all these details together, we can get a DOM XSS vulnerability in proxy page after sending a message containing a JavaScript URL, which will be put, as we mentioned, in the action attribute, and then the form will be, and then the form would be automatically be submitted. The following code contains a way to chain all weaknesses found. Here, as you can see, we would set a tab URL to JavaScript alert one, a simple poke, of course. Facebook fixed all vulnerabilities by making action attribute only accept HTTPS links or URLs, and also not using post message method in redirect.php anymore. I got $25,000 for this bag. Link to the full write-up here would be found here. Injection attacks. Ejection attacks differs on the client side from the server side. On the client side, the places and types of injections are limited. We have the ability to inject CSS, JavaScript, or HTML. In all of these cases, the injection does not necessarily lead to adding or running JavaScript code, or in other words, XSS. But the injection could only help us, for example, to extract valuable information as tokens or CSRF tokens or user information. Types of injections, as mentioned earlier, mentioned earlier, any injection point in a HTML page, JavaScript code, and even in CSS can lead to potential abuse. First example, HTML injection. The malicious user is able to control an entry point and is able to enter random HTML code onto a web page. This vulnerability can have many consequences, such as allowing an attacker to modify the page content and use it to launch phishing attacks. This is the simplest form of attacks. We should mention that HTML injection may lead to XSS, but not always. And thus, this name given instead. I mean, the name HTML injection was given instead of XSS or cross-site scripting. Possible attacks will be demonstrated in case running JavaScript code was not possible. Example code here. Here, an external script has been added that contains a function called DOM Purify, as you can notice in where is this? The red part here, which is one of the most famous and safest ways to sanitize or clean codes from JavaScript, for example, and enable HTML only. Of course, it depends on arguments passed to this function. We have the source here, and it's the query part of the URL, source of, as we talked before, the source and things. The source here is the yellow part, the tracking object with which reads the location.search and assigns a key value pair to that object from the current URL. What else? Here we have also document. This is a potential sync document via inner HTML. We sanitize what we had extracted from the URL and appended to inner HTML of an element with ID tracker. Here we can't get DOM XSS, unfortunately, even though we control what is written to the page via inner HTML, simply due to DOM Purify. So we have partial HTML injection, and we'll try to exploit it. Example code that can be injected onto the page. Here's a simple attack of phishing attack. We'll focus on the second attack here. This attack is complex and even requires a separate like chapter, but for the lack of time, we will explain it here in a quick way, but summarize its concept. Here we'll use an attack famously known as DOM clobbering. It is an attack that allows us to add variables to the window object, global variables, which is the object that represents the window, and in it we find the global variables that we created. This is possible because the elements or tags added to the page or document have some attributes like name or ID, and the content of these attributes becomes a variable in the window for easy recall or use of the tag. As an example here, we create an A tag with ID A tag 1. Later, if we use console.log window.a tag 1, we should have we should return a reference to that tag. Here also we notice that there are some window.config has its content either window itself, window.config, because we have or a new created object. Here we have this style of coding because to avoid that window.config was defined before. So either it's window.config, or we create a new object with this with details below, like version 1.2 test set to false and test path set to that. Since we come from the previous example, we can like put config instead of a tag 1. Like the previous example, we set a tag 1 the name, the ID of an a tag. Now we can replace a tag 1 name with config, This means that we have window.config now defined, and because of the or here, the first option is chosen, which is the one that would be the window.config will now represent the element, the A element that we create that has the ID set to config. Of course, here this is possible because the definition of window.config is after the HTML injection part above in yellow. Also, since the tag does not have any JavaScript code, it will not be deleted with don't purify to sanitize. Here we're talking about the if we inject an A tag with the ID set to config to manipulate, to try to manipulate the window.config object. Example code that can change the content of a config. Here we have an A tag with ID set to config and ref anything. We can put content to config.test by placing content for the first attribute ID, then name. As here, ID was set to config, name was set to test. We can also put content in config.test path by placing the content of the ID itself, config, and changing the name to test path. As we can notice here, so ID equals config, name equals test path, and ref equals ysam sc.js. This is like the URL for the malicious script to be included in the page. Of course, this requires time to understand, especially DOM clobbering, which I'll try to do that. We can combine the two, although the two examples previously mentioned, although the ID must be distinct in the page, but this is oddly possible. So if we set ID equal config and in an A tag, then inside that A tag, we also specify ID set to config. It would somehow create a confusion and or I'm not sure what it is called, document like two documents, two reference to a document element. Of course, by the way, this is a technique I think found by Turjank. I'm only here trying to explain it to you. We should mention that here config.testpath.ref has content or value and which is ysam sc.js. Let's go back to the first code and see what it does with config.test and config.testpath. So this piece of code in the top, we were able to both set test and also test path to this value. If we check here the code in the highlighted in red, we can see that testpath.ref was set to test module. Then we create a script element, then set the source of the script element to test module, and then append that element to body. Of course, here we have test config.test, and we also control config.test path, which means we can now inject code, inject JavaScript code by including a malicious script, external script, linked to a script. Also here we have an example of a partial HTML injection or cross-domain attack to steal data from the page in situations where an XSS attack is not possible. In the event that the application filters contained from methods that enable JavaScript to run, not like don't purify because it avoids this attack, or because we have rules in our CSP that prevent it. Here we have in the head of the page message listener, which would replace, would say the inner HTML or the HTML content of the header heritage with ID header to the message content. Of course, as we mentioned, we can't have XSS because it's blocked. JavaScript is blocked via CSP. Here we have a form that contains the hidden input and the CSRF token. We try to steal that. We know that we can see that the action was set to index.php and not /index.php. And this is a common and serious error. Of course, if you have a partial HTML injection, there is a tag that enables us to change the URL used in the document in the absence of the domain part of any URL. Similarly, in this case, in the action attribute case or the URL set there, if the tag base we can use the tag base. Of course, if it's not used, it would set the origin or domain of that URL to the current one. So, example of the attack code here, we send. We open the window containing the previously shown code, verbal code. Then, after opening that window, we instantly start post message to use post message or sending cross window messages to that window and setting base ref to attack a website. What would happen here that we can go back. The form action is automatically submitted after 10 seconds. So now it would submit this form to attacker website /index.php and with including the CSRF token. And this way we can steal the CSRF token of that page, then launch other attacks like to change password or add email and then take over the account. Okay, we have JavaScript injection. We'll pass that. It's basically XSS. CSS injection. Most people think that being able to run JavaScript code is the only way to exploit the bug. In that case, an ejection bug. This attack, in the event that CSS styles can be added via a link or directly to the page contained, enables us to steal information from the page without need to add HTML or JavaScript. There are different types of CSS attacks, but we try to only show a few examples. Here's the code as you may see. The vulnerable code here. We have a source that would read the current URL then it will insert a style sheet or a link to a style sheet or a CSS file. So here we can inject any CSS style in the current page. What we can do, we can add the following CSS code, which would basically do this. If the input with name password has a value that starts with A, we would require the background color set to this URL. This URL would log the current try A with logger.php A. If this is correct, of course. If not, it would try every letter, and after that we can try the next one and the next one until we find the full password. This is just an example of an attack. Question, sorry, wasn't able to show more attacks due to the limit of times. I can accept questions now.